This is slide number 25 and I am your presenter Asloob Mudassar. Here we consider an example in order to develop a relationship between the spatial frequencies in an object and its Fourier frequencies. Let's consider an object O4, function of xy. So here is defined as chi of xy into e to the power iota phi is the phase vector. So chi is an amplitude as a function of xy and phi is a phase vector as a function of xy. So O4 is an amplitude and phase object in the transmission mode. Chi amplitude distribution at the object plane, phi of xy is the phase distribution at the object plane. Chi is a constant for the given object. As you can see that there are no amplitude variations. Phi of x will determine the spatial frequencies. The phase varies from the front edge to the last edge. The spatial frequencies along the x and y axis, which we designate as f0x, f0y, for an object with a constant amplitude and noticeable phase variation are defined as. So here these are the definitions. F of f0x is equal to 1 over 2 pi, the rate of change of phi with respect to x, and along the y-axis we have f0y is equal to 1 over 2 pi into curly phi over curly y, that is the rate of phi along the y direction. Both will be represented as LP, that is line pair per millimeter or cycles per millimeter, and here the cycles mean that for example from dark line to white line and then again dark line, so this completes one cycle. Let's consider an example in the explicit form. Here we have defined object number 5 with amplitude equal to 1 and the phase factor e to the power iota 2 pi. Within the bracket we have a mu x into x plus mu y into y. So this is an object 5 where phi is equal to 2 pi into mu x into x plus mu y into y. So we have the value of phi over here, and we can put the values of phi in these formulas, and then we can obtain the value of f0x and f0y we have found over here. So f0x is equal to mu x and f0y is equal to mu y. So these are the spatial frequencies in the object. So O phi has fixed spatial frequencies along the x and y directions equal to mu x and mu y respectively. Now for the Fourier frequencies we have to calculate the Fourier transform. So the Fourier transform of this one is given by, you see that in the first line we have capital O5 on the left hand side, which indicates that it is the Fourier transform of the small object represented by O5 of xy, and you know that we have used Fourier variables fx and fy, and the integral is given as so you see that in the integral we have plugged in the function O5 as a function of xy. The rest of the parameters of the Fourier integral, you are familiar with that one. So now we in the second row we put the value of the O5, which is e to the power iota 2 pi mu x into x plus mu y into y. Then we combine the x values in the exponential form and the y values in the exponent, and then we separate these two as two integrals. One is the integral on the x variables and the other is integral on the y variables. So this is the separation of variables in terms of integrals. Now you know that the first integral is actually delta of fx minus mu x, because delta for mu x fx minus mu x, if you set fx is equal to mu x, then delta you know that is non-zero at that point, otherwise it is 0. Similarly, if you in the integral, if you set fx is equal to mu x, you get e to the power 0, which is equal to 1, and the rest of the integral will give you the same value as infinity, a very large value as the delta function will give. So we have written these these integrals in terms of the delta functions, delta of fx minus mu x, and the integral on the y variables is represented as delta of fy minus mu y, and both these delta functions are one-dimensional delta functions. We can combine them into two two-dimensional Dirac delta functions as a delta of fx minus mu x comma fy minus mu y. So the Fourier frequencies over here, because the delta functions will be non-zero when we have fx is equal to mu x and fy is equal to mu y. So these are the Fourier frequencies. So O5, that the object O5 has Fourier frequencies along the fx and fy directions equal to mu x and mu y respectively. So the Fourier frequencies are defined in the Fourier plane, and the spatial frequencies of the object are defined in the space domain on the x-axis on the object plane. So you see that now we have this result with us, that is fx Fourier frequency is equal to f0x equal to object frequency in the x direction, and both are equal to mu x. And on the right hand side we have fy, which is the Fourier frequency along the y direction, is equal to f0y spatial frequency of the object along the y axis, that is, and both are equal to mu y. For O5, which is the function of xy, the spatial frequencies at the object plane are equal to the Fourier frequencies at the Fourier plane. Fourier frequencies are localized to the limited space in the Fourier plane, whereas the size of the object is infinite. So here you see that in this, for this particular object, we have found that the spatial frequencies in the object are the same as the Fourier frequencies in the Fourier plane. So in this particular example, the object frequencies and the Fourier frequencies are the same, are equal. But you know that the Fourier frequencies are localized, because the Fourier frequencies are equal to mu x and mu y. But if you look at the size of the object in the integration, where we have evaluated the Fourier integrals, and you look at the limits, both limits on the integral are from minus infinity to plus infinity. It means that the object O5 has infinite extent. So object 5 has infinite extent, but its Fourier transforms are localized to certain regions. Mu x is fx is equal to mu x and fy is equal to mu y. This is the end of slide number 25.